I am Cal, and I'm on Team 7129, the Robo Raiders, and this is
Scott. I'm a 7129 alumnus and currently working as a systems engineer in the industrial controls field. I'm also a programming mentor for FTC.
Today we are going to be talking a little bit about object-oriented programming for FTC. And welcome to...
So the purpose of this video is really to provide an introduction to object-oriented programming within the framework of FTC, specifically using Java and Android Studio for the examples. It's a condensed version of the object-oriented part of the training that our new programmers go through the summer before the season starts. So it's really for those who have done some simple FTC programming but are looking to take their software development to the next level. The first question is, what do we mean by object-oriented programming, and why is that something that we should be using? Ultimately, it's a way of organizing our code to mirror physical or conceptual objects. We can take all of the code related to the drivetrain, for example, and group it together. This modularity gives us a couple of benefits. In development, the project can be broken down into smaller, independent parts. We can have one programmer working on maybe the drivetrain control system, while another programmer is writing the code that will control an arm or a lift. It also makes the testing process a lot easier. We can test independent and individual objects, and if something is failing, we don't have to scan through hundreds of lines of unrelated code just to find the parts that might be causing the problem. We can go right to the object that is failing and be looking at everything related to that and only what's related to that. We can also reuse code from year to year. If last year's robot had a subsystem that was similar to something that's being used this year, there's a good chance that that code can be reused. And as we build up a sort of library of subsystem code from year to year, we can mix and match those parts to get whatever the current robot hardware looks like.
So if the object-oriented programming, as an alumni, how have you seen that kind of evolve over the years, and how has that affected your team? I know as not personally a programmer, but I have seen it in use over the years, and it's also been very, very effective. But how have you seen it kind of evolve and affect your team over the year?
So when I think back to when I started with programming, we're still using Robot C, which didn't really give us a good way of approaching anything object-oriented. I think one of the things that has really been amazing is how, as the sort of FTC technology has improved and how teams have been able to adopt these object-oriented principles, we're seeing the coding and the capabilities of the programs get much, much better. And I think a lot of it has to do with that reusability from season to season. It used to be you started every season pretty much from scratch in the coding area where you were redeveloping a lot. I think now we're seeing a lot of teams that are starting to build up a code base where they have all of their drivetrain controls and a lot of their other subsystems programmed so that they're starting off the season not having to rebuild basic controls, but improve those and incorporate more advanced features.
And also, just as like a builder who visualizes and sees everything the programmers do, as a person whose old team didn't use object-oriented programs, so each year we were adapting and having to make new code. It's for a new team highly suggested because like you said, it's easy to debug, figure out your problems, and then you can also reuse it from year to year. So it's very helpful.
This really boils down to two core concepts for its implementation: classes and object instances. Classes we can think of as a sort of template that we have as a conceptual idea, but not necessarily the exact or specific implementation. They can't actually do anything because they don't know a lot about the hardware specifics. They shouldn't have the information about like the wheel diameter, the wheelbase, maybe not even how many motors are on that particular subsystem. Similar to how we might have a template for a marketing email, we have one template, and depending on the situation, we can fill out a bunch of fields to create the actual email that's going to be sent out. The instance represents the actual implementation of the object in hardware. When we want to use it, we give it the parameters that it needs, maybe some information about the type of encoders, gearing, or wheels, and the instance will be able to use those to do what we actually want it to do.
So what are some examples of, because when you're talking about your core concepts here, you bring up your classes. So what are some common classes that teams use?
Yeah, so one that I've seen pretty much every team use every year is a drivetrain class. Most robots have a drivetrain. So we're kind of breaking this into mechanical subsystems. So drivetrain's a pretty common one. A lot of times robots will have some sort of like linear slide lift. So that's another subsystem that you can consider, bundling all of the code into a class. Arms, camera scanners for if you're using like a webcam for analyzing the field. Anything that you can really package and think of as a single like hardware subsystem becomes a really great way of organizing your code into a class for that. That's a pretty high level overview, so let's dig in and take a look at some of the actual parts. Here we have the code for a class on the left and some autonomous code using an instance of that class on the right. We can note that there's a lot more going on with the class than the code that's using an instance of that class, so we'll take a closer look at that. We see three main parts to a class: the attributes, the constructor, and the method. Attributes, also sometimes called instance variables or data members, are variables that exist within the class to store information that's going to be used elsewhere. A good approach is to use them to store values so that you only have to perform calculations once, or store the current state of certain hardware so that it can be referenced throughout the class without any extra code. The constructor is a special type of method that initializes the class. This is where you want to specify the parameters for things like hardware-specific info. Something to note, the name of the class, in this example, drivetrain, needs to match the name of your class. That's what makes it a constructor. The constructor executes whenever you create a new instance of the class, so it's a great place to perform calculations that aren't going to change over the course or the duration of a match. In this example, we're going to provide some values for the encoder ticks per revolution, the gear ratio, and the wheel diameter when we create an instance and use that to calculate how many encoder ticks per inch there are. It also will handle the hardware mapping of our class attributes, the DC motors for left drive and right drive, so that we can use those elsewhere in the class. And finally, the methods are where we actually get things done. That's where we'll write the code that will move motors, read sensors, etc. All based on the information within the class from either previously executed code like the constructor or parameters that are passed into the method itself. This is where we really see a concept called abstraction applied. Abstraction is when we take a lot of complexity and we're going to hide it under an easy to use interface. In this case, we have something like drive forward, where we then will just have to provide the distance that we want to go and the speed, which makes it really useful as you're programming your autonomous. The autonomous might use or call drive forward several times, so we want to make sure that those parameters wouldn't include things that aren't going to change, like the wheel diameter. We wouldn't expect that to change throughout a match, so that would be something that would be left to the constructor. Next, we're going to look over an overview of an instance of our class in action. On the right here, we have a short example of an autonomous that drives forward once the start button is pressed. Two lines that we'll really take a closer look at. The first is the instantiation. That's a term for when we create an instance of a class to use later on. It starts with the class name, which would be just like when we declare a variable, it's the type. Then we have the instance name, which can be whatever you want, but it's a good idea, like variable names, keep it descriptive and easy to understand. We then have the new keyword, which is what's telling us that we're actually instantiating a class, followed by the constructor and the given parameters. The next line, drivetrain.driveForward, is a method call. We start with the instance name, as declared in the line above. Then we have the period and the method that we want to execute, followed by the parameters for that method. We can see that once we have the classes in place, the actual autonomous becomes rather simple to write, read, and modify. Now that we've gone over some of the core concepts, let's address an approach on actually coming up with these classes and methods and how you can plan that out in a season for your software development. We hear a lot about the design process in terms of mechanical design, but a lot of times we overlook how it applies to software. The same steps can essentially apply to our software design and provide a good framework for planning out the development of the controls on your robot. Starting with the strategy and the robot needs definition, Strategy part doesn't really change much from hardware to software. It's figuring out what you're doing on the field, that sort of thing. When we get into defining the robot needs, it's a little bit different. We're looking more in terms of control needs. So it's going to be things. Common one is like be able to move forward a specified distance within a certain range of air. There can also be more strategy-specific needs, and this is really the time to define everything that your control needs to do. Next, we have idea generation. Many control solutions have straightforward implementations. It can sometimes seem difficult to get innovative if you're just trying to move a robot forward. But taking the time to think about maybe some unique sensors can really be beneficial. Having some unique choices and things like sensors can lead to simplifying the code. So don't always jump straight to coding. Take the time to do some research and do some idea generation.
So with idea generation, how do you think a team, because you brought up like we're bringing up ideas of what sensors can we use to accomplish this or that? How does a team exactly go about kind of knowing what are the right set of sensors for each idea or concept that they need a sensor to be able to do that task? How can they break down that to make that easier?
Yeah, so I think the first thing to do is when you're approaching your strategy, approaching it with a sensor-heavy mentality is always a good approach. You should have, when we're talking about the robot needs, you should be including on those some sort of range of error based on the field itself. We need to be able to move forward towards this thing and be able to, be within 1 inch of the stack of cones. Well, when you have that criteria in your robot needs, that's going to start giving you indicators of where you need sensors. Perhaps your range of error, your plus or minus, is enough where simple encoders is sufficient. Perhaps it's something where you need to be really precise, and now you're going to start thinking, okay, what kind of sensors could we use in this situation to meet that precise range finding, distance sensing, whatever it may be. Once you have those sorts of criteria where okay, we're going to need a sensor that can be pretty precise here, that's when you start doing a lot of research. What's being done in other robotics applications? What are other robotics teams using, whether that's FTC, VEX, FRC, FLL, whatever's out there. Lots of research can really, a lot of times, give you some outside the box ideas for sensor use. And that's really what can set apart your programming, both in terms of performance and also to judges.
I'm going to give an example of how our team has kind of used that this year. So for autonomous, we want our team to be able to make cycle times within 1.5 to 2 second cycle times of grabbing a cone and then placing it on the load junction for the first meet. So once we had that criteria set and that goal of we want to be able to complete, or that target set that we want to be able to complete that task, then we can start researching, okay, so with our basic robot needs, what sensor could help us accomplish that? Could possibly a potentiometer sensor, something that can, because we have a turntable on our robot to help us get that position, but also for it to be precise enough every time. So that's kind of an example of how we've used it to then break down that and be like, okay, we have the set target of what we want our robot to be able to do. Now, what sensor or what systems can we use to now make that faster? It's very similar to like your design process and your idea generation for that. What is the best system, or what's going to allow us to be able to accomplish this target best?
Yeah, a lot of times, the design process applies to more than just mechanical. It applies to software too. But unfortunately, I think a lot of times that does get overlooked. So it's really just important to kind of make sure that you're still applying it. Next, we have the conceptual design. This is where we're going to be flowcharting and defining our class structure. Basically laying out every step that the robot is going to have to take to achieve the game strategy that you defined. Flowcharting will give us a list of actions which the robot has to make, which will really help when you're getting into the next step, which is class definition.
For like conceptual design, when people are starting to begin their flowcharts for object-oriented programming, how much do you think you need to break down each step for your flowchart? Do you create your basic flowchart and then you break it down from there, or do you create a very detailed flowchart from the beginning in order to get all your movements down?
So I would recommend mapping out the entire path that you want to take at a detailed enough level where you're going to be able to see the direct correlation from end result to where your flowchart started. You don't want to get too bogged down in necessarily defining sort of sub-steps of single actions. Ultimately, the purpose of this, we don't want to get into implementation yet. The purpose of this is for us to start laying out the steps that we're going to take so we can be defining the methods of the classes. So you want to sort of be having your steps be similar to the methods in your classes. So we're going to, on our flowchart, we're going to have something that's like drive forward 50 inches. That's the single action. That's how far we're going. We're not going to be so concerned about, first step in the flowchart is going to be setting motor number 1 to run with encoder. The second step of the flowchart being setting the target position to X, Y, Z. We're more concerned with the sort of big picture. What are the steps when we're thinking of it in terms of what does it mechanically actually have to do? Class definition is when we're actually going to take that flowchart and you're going to start grouping it by what kind of subsystem is performing the action and what is the action that's being taken. In this example, we can see we have in our flowchart driving from drivetrain mentioned, we have lifting and arm mentioned. So we're going to group those into 2 classes, our drivetrain and arm. And each of those has a single action that it's taking in this simple flowchart. Driving forward under the drivetrain and lifting the arm under the arm. Once we have that list of classes and methods, the next step is to actually start doing the implementation of the prototypes. So prototype development, we're going to call it prototyping because it maintains the parallels to the mechanical design process, but you can't really think of this as quite as temporary or disposable as you might normally think of prototyping. With code, it's easy to constantly be making improvements and it can eventually become something permanent. We're going to take the list of classes and methods from the flowcharting step and begin implementing them in actual code. This is going to require a lot of testing, a lot of debugging, as you figure out how each of these is actually going to be implemented and how it's actually going to work. Once you have that working, though, we can move on to the solution completion. You can use those methods, you can use those classes to execute the actions that you've specified in your flowchart to complete your program. In this example, we instantiate our drivetrain and arm class, and we make 3 method calls that executes each of the steps described in the flowchart. That's the summary of how we can use object-oriented programming and a defined design process applied to our software to give us object-oriented programs that can be flexible and modular and easily reused from year to year.
Thank you all for being here, or thank you for joining us. Good luck with your season. Also, thank you, Scott, for giving a basic overview of object-oriented programming.
And scene.